Oh, I love working on videos. It's so fun to be writing a script right now. Man, I should probably take a break from working. Maybe I'll watch a movie. You know, what can I put on real quick? Okay, let's see what I pick here. Oh, you know, we gotta do Jurassic Park. Like, come on now. I can't wait to watch this movie. What's good, Terry? Okay, we're at the Brachiosaurs. Oh, they're so big and majestic and... Wait a minute.
We're gonna make a fortune with this place. How fast are they?
I wonder,
T-Rex is 32 miles an hour.
could sauropods stand? And that's the question we're asking today. Hello again and welcome back to the Paleo page. My name is Connor, and this video idea came to me from a question I asked myself about a month ago during my 478th rewatch of Jurassic Park. This video was originally meant to be super quick and easy, potentially even a short form video. However, as I went on to research whether a sauropod could actually stand up, I began to understand very quickly that this topic is not really that simple. So here we are now, it's a long video. While the sight of a Brachiosaurus standing up on its hind legs has been made famous by Jurassic Park, the idea of this has been around for a lot longer than that. In fact, sauropods, assuming this stance from what I could find, have their origins all the way back in the mid to late 1890s. In 1897, the American Museum of Natural History sent out a team to the Coma Bluffs in Wyoming. This location was famous for its remarkable dinosaur finds, but it was also thought to have maybe been exhausted of its fossils due to the team sent by O.C. Marsh back in the Bone Wars. However, when the AMNH team got there, they found something incredible. Barnum Brown, the paleontologist famous for discovering the T-Rex half a decade later, as well as Henry Fairfield Osborn, discovered a giant femur, or the big bone in your leg. This femur then led to the discovery of a beautifully preserved back half of a sauropod dinosaur, at the time called Diplodocus longus. This specimen preserved most of the back half of the animal, including the pelvic girdle, some of the spine, and a majority of the tail. When writing about this discovery in 1899, Osborn had a very interesting idea that he wrote down into the final publication. He wrote, in quotes, "The tail, secondly, functioned as a lever to balance the weight of the dorsals, anterior limbs, neck, and head, and to raise the entire forward portion of the body upwards. Thus the quadrupedal dinosaurs occasionally assumed the position characteristic of the bipedal dinosaurs, namely a tripodal position, the body supported upon the hind feet and the tail." Sauropods standing on their hind limbs in fact started out as a scientific idea. This idea of sauropods standing up on their back, legs, and tail, which we call tripodalism because three things supporting its weight, three limbs, leg, and tail, then went on to inspire countless reconstructions and interpretations of these animals. Paleo artists like Charles R. Knight depicted sauropods in this stance. The famous Barosaurus, also in the AMNH Rotunda, is in this position. Of course, Jurassic Park depicted its Brachiosaurus standing tripodal to reach a tall tree, just like I have here. Walking with Dinosaurs showed its Diplodocus doing this, and even in more modern paleo media they show this, such as in Prehistoric Planet, where they show the two male Dreadnoughtus doing this in order to fight over the breeding rights of the females. Now, while it is a scientific idea, sauropod tripodalism is a very old scientific idea, and this was all the way back in 1899. Science and our understanding of paleontology and dinosaurs and biology as a whole quite obviously has evolved significantly over the past nearly century and a quarter. So, with the most up-to-date science and research, is sauropod tripodalism even possible? Because, I don't know if you've noticed, but sauropods are really big. They were massive. Assuming this position would be a massive strain on the bodies of these animals, both in the legs of course, but also in their spines and the hands, and pretty much the entire body to be fair. So, could sauropods go tripodal? The answer to that question is, drumroll please, it Depends, I guess. Now what does it depend on? Well, two things. The first variable on whether a sauropod could stand up and go bipedal or tripodal is about where a majority of the animal's weight would have been located. This is known as the animal's center of mass. A study from 2009 looked at how the centers of mass for two different sauropods, Diplodocus and Brachiosaurus, would have affected their ability to go upright. The study is sadly very short, it's a single page, but the results show that Diplodocus would likely be more able to go tripodal because its center of mass would have been closer to the back of the animal, near like the pelvic girdle area. Brachiosaurus, however, would not have been great at going tripodal, because its center of mass was a lot farther forward, near the sort of like chest of the animal, making it very unlikely that this animal would have been going in these stances, and if it did, it likely wasn't doing them for long. However, center of mass is not the only way to determine whether a sauropod could stand up. To truly see whether they could, we need to look at a second variable, biomechanics. Now please bear with me because biomechanics are so confusing, and I'm still not even sure I fully understand how this research was done. But I will try my best to explain it to you the best I understood it. Anyways, a study from just last year, 2025, so I can, date the video, looked at the biomechanics of the femora of multiple species of sauropods from across the entire sauropod family tree. Using a test known as finite element analysis, they looked at how going onto the sauropod's hind legs would have stretched the femora or femurs of these sauropods. The sauropods they chose include Diplodocus, Amargasaurus, Giraffatitan, Dreadnoughtus, Uberabatitan, Australotitan, and Nuquinsaurus. A wide range of animals, from Brachiosaurs to Diplodocus to Titanosaurs to Saltosaurs, and this makes it easy to compare the sauropods' standing ability evolutionarily. The researchers tested two different scenarios to determine how effective the back legs of these animals would have been at reducing stress. They first tested an extrinsic scenario to simulate femoral loads. All femora were 3D modeled in Blender and placed into the computer and scaled to 1 meter. Stresses were applied at a node at the medial portion of the femoral head. 10 tons were applied for all of the femurs, and the total loads were calculated by multiplying mass by the gravitational acceleration. Restraints were also set across the femora to standardize angles and achieve a 0 degrees of freedom. Now, stress was only applied to the hind limbs, not accounting for the tail since tripodalism is unknown, but it should be noted that the tail likely would have helped in going into this position in real life, but these tests are for comparison rather than to find absolute metrics. The second scenario that they tested was intrinsic. This test was to look at how the muscles around the femur would have dealt with the stress from holding up the entire animal. Muscles tested on all of the femurs include the cauda femoralis longus and brevis, femora tibialis internus and externus, adductor femoris 1 and 2, as well as a couple others. Anatomical correlates, or femoral attachment scars, determined where the muscles were placed on each femur. The original scales and sizes of the femora were used for accurate calculations, and the loads were applied to each respective muscle section along the direction the muscles would have been facing. Now, that's all really complicated, really awesome. But what does any of it mean? What does it mean? I can tell you. In the extrinsic test that looked at the bones themselves, all femora tested showed a similar amount of stress in these same areas. Most stress was endured by the femoral head and the distal third of the femur. This showed that stress variation occurred more in how much stress the bone was taking, rather than where the stress was located. Nuquinsaurus and Uberabatitan had the lowest mean stress values of the selected specimens, while all the other specimens exceeded the mean of 1.9 MPa. The specimen that was under the most stress was the femur of Dreadnoughtus. For the other intrinsic test on the muscles, it also showed that there was more variation in the magnitude of stress rather than where the stress was located. Uberabatitan did considerably worse in this scenario, but Nuquinsaurus again had the least amount of stress. Dreadnoughtus, on the other hand, also had the most amount of stress. In fact, the femoral muscles of Dreadnoughtus went through so much stress that it broke the scale of the finite element analysis. For the visual of the FEA, there was a maximum of 10 MPa to show for the visuals that they would use in the charts. Dreadnoughtus went over that by over 5 MPa. For reference, the second most stressed specimen was Giraffatitan, and it only scored a 1.9 MPa. Meanwhile, Dreadnoughtus scored all the way up at 15.67. God damn it, I said the thing. Put it in the comments, I don't even care anymore. Oh, you did the thing. Shut up. Now, I just said a bunch of numbers. But again, what does that even mean? What does it mean? Basically, Lower stress levels mean that sauropod in question would be more able to achieve a bipedal or tripodal stance, and that they would have been able to sustain it longer while they were up there. Nuquinsaurus had the least amount of stress of both tests, meaning that it was likely more able or capable of going tripodal or bipedal than the other sauropods that were selected for this study. Which kind of makes sense. Nuquinsaurus was a saltosaurid, and saltosaurids were a group of sauropods that had much shorter necks and smaller bodies than their titanosaur cousins like Dreadnoughtus. So they were already thought to have been well suited for standing up, which these results seem to support. Speaking of Dreadnoughtus, it had the most amount of stress in both tests, especially when looking at the muscles. So unlike what Prehistoric Planet showed, Dreadnoughtus likely was not very capable of going into this position without, shattering its femur muscles. Now, does any of this mean 100% that a sauropod could or couldn't have gone in this position? No, not really. There are still a lot of things to consider, especially in this study. Things like cartilaginous tissues would have reduced the stress placed on the bones significantly, and pads on the bottom of the feet would have also absorbed some of the stress applied. Or even if they had something to prop themselves up, like a tree or a rock, or their mates, for instance. In the end, though, it does seem that at least some sauropods would have been able to go into this position. That some sauropods would have been able to stand. However, the real question isn't whether these animals could stand, but whether they actually did stand. Why would a sauropod need to go bipedal or tripodal? Why would a sauropod need to be able to go into its hind legs? The most common ideas for why sauropods could have assumed this position include for things like feeding on higher food sources, it maybe being a defensive display, or maybe they would need to mount their mate in this way. However, is there any actual evidence for sauropods actually achieving this posture? And the answer to that question is, again, not really. A study was published back in 2005 that looked for pathologies that would indicate bipedal or tripodal positions within sauropods. The reasoning behind this was that getting such a massive animal up into that position would have been super strenuous on the backbones, the vertebrae. And when going back down into a quadrupedal position, there would be a massive impact on the hands and fingers of the forelimbs. The researchers argued that these areas would show signs of stress fractures in the fossils of these animals if they indeed did assume a tripodal or bipedal position regularly. So, they examined the spines, hands, and feet of 13 different species of sauropod to look for abnormalities. And then once they found these abnormalities, they looked at them all and determined whether or not these abnormalities were representative of stress fractures. Through this analysis of the fossils, they found that stress fractures were only found on the metatarsals of the back feet. Now there were 2 stress fractures found on the fingers or phalanges of 2 sauropods, one on Apatosaurus, one on an animal called Neurosaurus. But they reasoned that these stress fractures would have been from an injury rather than going bipedal or tripodal and then going back down to quadrupedal stance. There were no stress fractures on the vertebrae examined. Other than those 2 from injury, there were no stress fractures on the hands examined. The stress fractures being so prevalent on the back feet was attributed to how the sauropods were walking, with the majority of the propulsive thrust of their walk coming from the hind limbs. However, with no stress fractures on the hands or spine, it was reasoned that these animals were not standing. Just because these animals were mechanically able to go in this position does not mean that they actually were going in this position. The authors gave the example of just because a human skeleton is biomechanically able to swim, that does not mean that every person knows how to swim. And it was likely the same with sauropods standing. Until some other researchers then went on to argue that if standing was a normal behavior, then it would not cause stress fractures. So what evidence would settle this debate once and for all? Well, maybe some sort of foot tracks, ichnology showing a sauropod going bipedal or tripodal before coming back down to the ground would do it. However, as far as I can find, we don't have anything like that. So to answer the question of the title, could sauropods stand? I mean, probably. It depends on the species. Yes. Did they stand? We really have no idea. From the evidence we have, maybe not. But, they still could have, but they maybe didn't, but they maybe did, and could they? Again, it depends. Is that really a satisfying answer? No? Well, sometimes things in science and paleontology remain mysteries. However, that's not really a bad thing. It just means there's more research to be done, and there's more things to learn. And just maybe one day we might find a track print from a sauropod, maybe in the Jurassic or the Cretaceous, that shows an animal standing on its hind legs, just like the Brachiosaurus in Jurassic Park. Now, we're finally at the end of a video. I hope you learned something because I know I did. If you did learn something, or if you just enjoyed the video, then please feel free to leave a like. Not only does a like tell me to make more videos just like this, but it also pushes the video into the algorithm so a person scrolling on YouTube can learn something rather than watch some AI-generated slop content. If you want to get to know me a little bit more for whatever reason, be sure to check out my socials, all linked in the description below. And finally, if you like all things paleontology and dinosaurs, feel free to subscribe for more. I'll see you next time, and credits. Oh yeah, I'm gonna do the thing. Control-Shift-C. Did you know you can do that? Control-Shift-C shows you the word count. You can highlight all the things that's actually script and not references. So I do my references on the same page. 2,451 words, wow. Yap. I did. I already have the next video or two planned. I'll see you when they come out. I don't know when this is coming out, to be honest. It's probably gonna come out Wednesday. Or maybe Friday, or July, or Tuesday, Mother's Day, Christmas Day, I don't know anymore. Vulture Awareness Day, I need to do another video with them. That'd be awesome. I'm deciding what the next video will be. It'll either, I think I need to do a topic that's not dinosaurs real quick. The credits are already probably done, so we're just gonna go to an end screen. You're in an end screen! You can click this video to go watch it. Or, hear me out, you could subscribe. That would be awesome. That'd be really kind of you. That'd be so kind. I would be so grateful if you did that. And if you liked, and alright, I'll see you next time. Bye!